Good morning, Internet. I am Matt Buyak, and in this video, we'll take another look at problem 24 from the Project Euler problem archive. So in the last video, we solved this problem using a simple C++ program. And I had intended to move on to doing a video on addition of big integers. But then I realized that we can actually solve this problem using analysis alone. And so that will be the subject of this video. So just to refresh your memory, this problem asks us to find the millionth permutation of the digits 0 through 9, where a permutation is just an ordering of the items in question. You'll see that it gives, as an example, all the possible permutations of the digits 0, 1, and 2. And so let's get into it. As usual, we'll open up our analysis file for problem 24. OK, so let's start with the most basic question. How many permutations are there on n items? And so we'll start by considering a simple example. We'll say, consider permutations of 0, 1, 2, 3. So rather than starting with the full set of digits, we're just going to look at the first 4 digits. And you might note that when we're constructing our ordering, our permutation, we'll need to pick a first item, and then we'll need to pick the next item, and then we'll need to pick the next item. And that will have, in particular, note there will be 4 options for the first item, 3 options for the second item, 2 options for the third item, and only 1 possibility for the last item. That is the number of possible permutations will be 4 times 3 times 2 times 1, which is equal to 4 factorial. If we generalize from this, you can see that the number of permutations on n items is just n factorial. That is n times n minus 1 times n minus 2, all the way down to 1. OK, so before moving on, you may just note that this matches the example that's given. These are all the permutations on 0, 1, and 2. And there are indeed 6 of them. That is 3 factorial. OK, so now the next question we might ask, next question, what is the first permutation in on a set? And the answer is just going to be the items are in ascending order. Note that for 0, 1, 2, 3, that is 0, 1, 2, 3. And you can see that this is true because, for example, if it didn't start with a 0, if it was a 1, 2, or 3 in the first position, that would necessarily be a greater number than 123. And same with any other position. If suppose for the third position here we had put the 3 there, well then it would be 132 rather than 123. So again, that would be a greater number, so it couldn't be the first permutation. And a related question, what is the last permutation on a set? And you might guess it. It's just going to be, the items are in descending order. That is, 3, 2, 1, 0 for the items 0, 1, 2, 3. And you can make a similar argument where, if any other digit were moved into the first position, it would necessarily create a smaller number, and so no other permutation could possibly be the last permutation. Okay, so now we get down to the real key question. We'll say, key question. How many permutations come before a particular permutation? Note that our problem 24 can be rewritten to find the permutation which has 999,999 permutations before it. And so this is really the key question to solving our problem, is if we can find how many permutations come before a particular permutation, then we can find the permutation that has exactly 999,999 permutations that come before it. Let's see. We'll say, in particular, consider the first permutation on 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which begins with a 5. This isn't specifically required to solve our problem. This is just an example to get us thinking about this key question here. Okay, so first of all, which permutation is that? That is, what is the first permutation that begins with a 5? Note that it must be a 5 followed by some permutation on 0, 1, 2, 3, 4, 6, 7, 8, 9. I left off a 0 here. And we already know what the first permutation on this set is. It's just those items in ascending order. We've already answered that. That means the first permutation, which begins with 5, must be 5 and then 0, 1, 2, 3, 4, 6, 7, 8, 9. So a 5 and then all the other digits in ascending order. Yes. Okay, so now how many permutations come before that? So we'll say, note that any permutation which comes before this must begin with 0, 1, 2, 3, or 4. Also note that there are the same number of permutations which begin with a 0 as begin with 1, 2, 3, or 4. that is, well, I guess I don't have to type this out. That is the number of permutations which come before our permutation here is just 5 times the number of permutations that begin with 0. So how many permutations begin with a 0? Well, as I indicated when we were figuring out this permutation, a permutation which begins with a 0 is just a 0 followed by a permutation on 1, 2, 3, 4, 5, 6, 7, 8, 9. That is, there are 9 factorial permutations which begin with a 0. And this just comes from our conclusion, up at the top here, where we were figuring out the number of permutations on a given set. So here our set has 9 items. That means that there are 9 factorial permutations on that set. And so, therefore, there are 5 times 9 factorial permutations which come before 5, 0, 1, 2, 3, 4, 6, 7, 8, 9. And we'll just say, note 5 times 9 factorial is equal to, and let's pull up our calculator here. So 5 times 9 factorial. And that's going to be this number right here. So we'll say, just paste that into the terminal. And so you'll note that this is greater than 1 million. So we'll say, because this is greater than 1 million, our final answer cannot cannot begin with a 5, 6, 7, 8, or 9. It has to begin with some smaller digit. And using this technique of figuring out the number of permutations that come before a given permutation, or rather, a permutation which is the first permutation beginning with a given digit, we can figure out what range our final answer must be in. And so we'll say, note 0 times 9 factorial. Well, that's just going to be 0. 1 times 9 factorial. Say 1 times 9 factorial. Is going to be that number. 2 times 9 factorial is that number. And 3 times 9 factorial is that number. And you'll notice that now we've exceeded 1 million, or to be more precise, we've exceeded 999,999. You'll recall that we're searching for the millionth permutation, but that is, we're searching for the permutation that has 999,999 permutations before it. And so that's actually the key number here. Okay, so what does this mean? We'll say, therefore, our final answer must begin with a 2. Types 1. Okay, must begin with a 2. And you can see that's because the first permutation which begins with a 2, has 725,760 permutations that come before it. And so it must start with a digit that is at least 2. But if it were to start with a 3, the first such permutation is already greater than 1,000,000. And so we know that it must be a 2. Okay, so now how do we consider the permutations which begin with a 2? So we'll say, now consider just permutations which begin with a 2. How many such permutations come before our goal permutation? And so that's just going to be our target number, 999,999, minus the number of permutations that start with a 0 or a 1. And so that's just going to be 999,999 minus 2 times 9 factorial. And so pull up our calculator. Say 999,999 minus 2 times 9 factorial. And that gives us this number here. So we'll say, oops. Oh, something didn't copy over correctly. There we go. Okay. Therefore, we are interested in the permutation which begins with a 2 and has 274,239 other such permutations which are less than it. Okay, so now you'll notice that we've taken our problem and we've reduced it to an identical problem that is smaller in magnitude. And this is a common strategy in programming and in analysis. And so that is, originally we were looking at permutations on all the digits, and we were trying to find the millionth such permutation. Now we're looking at only permutations which start with a 2, and we're trying to find the 274,240th such permutation. And so this basically points the way toward a solution. We can just repeat this process, determining more and more digits until we have our answer. But we have to be a little bit careful in how we go about it. It's going to be a very error-prone process, and so let's make a little table here to help us out. So we're going to start with the items that we have in our list, and that's to start. That's just going to be all the digits. And then for our next column, let's have our target. And so to begin with, that was 999,999. Again, we're considering the number of permutations that come before, not the place number of our permutation. Okay, so next let's have the, we'll call it the index. That's going to be the number of, or the multiple of k factorial, which is less than our target. And k is just going to be the number of items here. And so that was 2 for our first iteration. And then we'll want the digit, and that just corresponds to, again, 2. Now you might wonder why I have two separate columns here for the index and the digit. You might guess based on our first pass here that those are the same, but it turns out that as we start to remove items from our list here, that that may not necessarily be the case. Okay, so for the second pass, we've removed a 2, and we have a new target here. So let's enter that in here. Okay, and now we can just repeat the process until we get our solution. And so before we were subtracting off multiples of 9 factorial. We had 9 elements in our set, and so now we need to subtract multiples of 8 factorial. And so say minus 8 factorial. So that's 1, 2, 3, 4, 5, 6. You'll notice that if we're down to 32,000 and change, 8 factorial is 40,000 and change. So if I were to subtract one more multiple, that would be a negative number, which is undesirable there. So we'll say 6. And here we can see an example of what I was talking about. So starting with the first digit is item 0. So we'll say 0, 1, 2, 3, 4, 5, 6. And that gives us digit 7, even though the index was 6. Okay, so just paste our new target here. And then our list of items is just going to be the same, but without 7. 7 has been removed. Okay, and continuing, we were subtracting multiples of 8 factorial, so now we're on to multiples of 7 factorial. So that's 1, 2, 3, 4, 5, 6. Again, our index is 6. That corresponds to 0, 1, 2, 3, 4, 5, 6. The digit is 8. Paste our new target. And we removed digit 8. Okay, we were subtracting multiples of 7 factorial. So now we're going to say minus 6 factorial. And it's just 2. So we say index is 2. 0, 1, 2 is going to give us digit number 3. Copy our list of items and remove the 3. Okay, we were subtracting multiples of 6 factorial, so now we're on to multiples of 5 factorial. And that was 5 multiples, so our index is 5. 0, 1, 2, 3, 4, 5. That gives us a 9. Our list is just as before without the 9. Our target is now, I believe it was 39. Yes. And now we almost don't even need our calculator anymore. Okay, so we were subtracting multiples of 5 factorial. Now we're down to multiples of 4 factorial. And so you'll note that that's 24, and there's just one multiple. So our index will be 1. Our digit will be 1. And so let's remove that from our items list. We subtracted 24, leaving us with 15. That was 4 factorial, so now we're going to subtract multiples of 3 factorial. That's 6. So we'll subtract 2 times 6. That's 12. Our digit, therefore, will be 0, 1, 2. Gives us a 5. We'll remove that 5. As I said, we removed or subtracted 2 times 3 factorial. That leaves us with 3. We're now subtracting multiples of 2 factorial. That is just 2, and there's just 1 of those. And so that gives us the digit 4. We subtracted 1 times 2 factorial. That leaves us with 1. Now we're subtracting multiples of 1 factorial. There is just 1. And so that the index of 1 gives us digit 6. That leaves us with a lone item of 0, a target of 0, an index of 0, and a digit of 0. Okay, so now we can read out our final answer, 278,391,5,460. Or in other words, 2,783,915,460. And going over to the archive here, we can see that that does indeed match our solution. Okay, so thank you for joining me in this video. In the next video, we'll be moving on to that before promised video on addition of big integers.